Hello class and welcome. So we'll continue our lessons on multi-stage multi-stage amplifiers by looking at the examples and problems. Last recording I walked you through the theory, the lecture as given in the textbook, with some extra introduction to um, multi-stage amplifiers in general. So it's time now to start looking at some of the examples and the problems. So on slide 83, this is the first numerical, and this is an example from our textbook. It's on page 653, and it relates to the two-stage CMOS op-amp. Remember, in our textbook, in this particular section of this chapter 8, we have two examples of multi-stage amplifiers. One of them was CMOS, two-stage CMOS op-amp, and another one was a four-stage BJT or bipolar op-amp, right? So this one, 8.5, relates to the two-stage CMOS op-amp. So we know that all of this area is stage 1 and Q6, Q7 and this capacitor is stage 2. So let's see what the question is. So consider this circuit and with the following device geometries. So W by L for all these Qs, and there's 8 Qs totally, 8 transistors, are given, right? Some of them are 20 by 0.8. Q4 is Q3, Q4 is 5 by 0.8 because Q3, Q4 are the NMOS devices. All the others are, most of the others are PMOS. This is NMOS too. Yeah. And then Q6, some of them are 40 by 0.8, 10 by 0.8. So they're all over the map. Also given is I reference, this value, 90 microamps. V for Tn and Tp, they are different. Then you have the K prime value for mu n, which is 4 times mu p. So that shows it's a matched set of devices. And then Va, the early voltage, is given to be 10 volts. VDD and VSS are equal and negative. So this is 2.5, this is minus 2.5 volts. So given all this, he asks you to evaluate ID, the drain current in each device, right, for all devices. The overdrive voltage, gate to source voltage, GM, and RO, the output resistance. Also find A1 and A2, which means the gain for stage 1 and gain for stage 2. The DC open loop voltage gain, which is the product of A1 and A2, the input common mode range, and the output voltage range. So the tricky portion in this problem to me is these last two items, the input common mode range and the output voltage range. So again, this is a solved problem. I advise you strongly, make sure you spend enough time going through each one of these steps in the solution. Like I said, this portion is pretty straightforward. It's a straight application of the formulas. Similarly, even A1 and A2 are pretty easy to find. So for example, ID, if you want to try it out for one or two of these devices, first of all, you must know right, which ID. So I reference converts to I, right? So in some of the transistors, the ID is nothing but I. So here it's Q5, it's I, Q7, it's I. But then in some of the transistors, it splits. So Q1 and Q3, it becomes half of I, right? So if it's 90, then you should take it as 45, right? 45 microamps in some of them. So make sure you put the right IDs, and he shows you actually in the table in the solutions. You can see where the 90 is split into, if it either retains as 90 or it's split into half, 45. I won't waste any more time. I tried one or two, they all work out okay, so there's no errors or anything, and you should be able to, he shows you the formulas for ID, for GM, for RO, and then also how to find VGS. Once you have VOV, you just add it to the VT. The first, the voltage gain of the first stage, GM into RO2 in parallel with RO4, that is minus 33.3. Second stage, same thing, it comes out to be minus 33.3. And the overall loop gain, he just multiplies it and it comes out to be 61 dB. So that portion is simple. In fact, I have a few more notes on this same example on my next slide also, where we have to find the input common mode range and the output voltage range, right? These are the two things to find. So the input common mode range has a maximum and a minimum value, right? So there's VICM, input common mode max, and a VICM min. So the lower limit is the VICM min, and he shows you how to calculate that. In fact, this sentence in red is from the textbook. He uses this to come up with the value of the ICM min as minus 2.3. I wasn't quite sure how we came up with this, so I wrote out some of my own notes. I ask you to go through this also, so that you're convinced that his derivation of minus 2.3 matches. So, to give another minute or two on this issue, the lower limit of the input common mode range is the value of input voltage at which Q1 and Q2 leave saturation. So where Q1 and Q2 leave saturation, that is the lower limit, right? Similarly, the upper limit is where Q5 leaves saturation, okay? Now these are PNP devices, so they're kind of opposite of how he defines the lower limit and the upper limit compared to what we studied, say, in slide 7. Here also we defined VCM max and VCM min. Here these were NMOS devices and the current source was at the bottom. So the upper limit, VC max, is what makes Q1 and Q2 remain in saturation. But if you look at this problem, and I'm going back to that slide, I think it was 84, yeah. If you go back to this problem, now the lower limit is what, because these are PMOS devices now, the lower limit is what leaves Q1 and Q2 in saturation, and the upper limit is defined by how Q5 has to stay in saturation. So I'll let you read through it, make sure you understand exactly the logic. But as far as the lower limit of the common mode range, first of all, let's look at our definitions of PMOS saturation, right? Either the D to G, voltage drain to gate, has to be less than VTP, or to put it the other way, V gate to drain has to be greater than minus absolute value of VTP, right? So let's use this definition. But to get this, the only thing we know is VTP, right? That's given to be minus 0.8 for PMOS device. So we need to find VGD, right? So for Q1, you need to find the gate to drain voltage. So to do that, you first need to find VD1, which is this point, right? Now this point is this VSS plus gate to source here, right, of Q3. If you add those two, you get VD1. And that VD1 is a negative value at minus 1.5 volts. So VG1, so for this here, to find the value of the voltage here, VG1, you can write the expression VGD1 plus whatever is at this point, VD1, right? So VGD1, gate to drain 1, plus VD1, and VD1 happens to be a negative, so you put a minus 1.5. From here you can find VGD1, which is gate to drain of Q1, to be this formula. Now for saturation, this has to be greater than this, right? This portion. So if I substitute that, I come up with this Vg1 greater than or equal to minus 2.3, which is what he calls the lower limit here. Okay. So I thought I'd just show you that calculation. The other calculations he shows are pretty straightforward, so I'm going to let you read through it. But this one seemed a little bit tricky, so I'm walking you through the logic of how to find this lower limit so that Q1 and Q2 just leave saturation. Okay. With that, I'm going to move on to problem 8110 from the back of the chapter. Now this actually refers to the same amplifier, multi-stage amplifier, as we just saw, but there is one slight difference in this problem. So what he says is, a manufacture error results in the W by L ratio of Q7. So look at this figure, this is Q7, right? So this Q7, previously it was given to us as having 40 by 0.8, which is similar to Q5 40 by 0.8, Q8 40. So these three are matched, right? Now, in our problem, what he tells us is they are not matched anymore. Q7 has a slight change. It came out to be 48 instead of 40. So if that's the case, then what happens, right? So as you can imagine, when everything is balanced, no unnecessary voltages appear and no amplification happens. But once you have some mismatch like that, then you can expect that what is called a systematic offset voltage will appear at the output because of this mismatch. So find that, right? That's what we need to do. Also, assuming that the open loop voltage gain remains the same, if you have a systematic offset voltage at the output, what is the systematic corresponding voltage at the input, the offset voltage? Okay. So I think we studied this briefly, and I'm going to just open up problem 8110, and this is in my PDF, chapter 8, differential and multi-stage amplifiers, part D, right? This is the very last one, class problems. So now W by L is now 48 by 0.8. Since Q7 and Q8 form a current mirror, so this Q7, Q8, Q8, Q5, Q7, all three form a current mirror. We can write, and remember the reference current is in Q8, so you have to compare, in this formula you have to use W by L of 8. I reference is 90. So what is happening is basically ID7 has 108 microamps flowing in its drain and not 90. Okay, that causes an output offset voltage. Now we have seen some formulas about this offset voltage earlier, but those referred to, in fact, we saw where Vt, the threshold voltage, can be not the same for many devices. That causes some offset voltage. W by L differences can cause some offset voltage. So we saw some of those cases, So here, but the formulas they gave us in the textbook was related to the input offset voltage. Now, actually on the, not the input offset, but the input devices. If there was a difference in Q1 and Q2, then we can use those formulas. But in this case, they are telling us that the problem is with Q7. Hence, those formulas can't be used directly, but we can apply some logic here, and that's what I'm showing you here. So the output offset voltage is the difference in the current multiplied by the output resistance seen by at this point, right? So at this point you have two output resistances and there's no load resistance, so we are only talking about the intrinsic output resistance of Q7 and Q8, right? So that's Q6 and Q7. So that's what you see in parallel, RO6 in parallel with RO7. Delta I is the difference in currents in the drains of the two output transistors Q6 and Q7. So delta I is 18. RO6 from the previous example we calculated as 8.5. Somewhere here in the RO6 for Q7 in the table is 111. I just checked. So that's 111. RO7 you can calculate as VA by ID, which is 92.6. It was previously 111, now it is dropped to 92.6. So the output voltage, the output offset voltage, is this delta current times this resistance, that is 909 millivolts. So once you have the output and you know the gain, you can find the corresponding input as the output by gain, and that's 0.82 millivolts. Okay. So that is problem 8110. We have one more interesting problem on CMOS, the two-stage. So this is problem 8108 from the back of the chapter. So you can see that we have a similar configuration as what we have studied. There is one stage, which is the differential input stage, that is stage 1. But in this case, these are these are NMOS devices, right? Q1 and Q2 are NMOS. In the previous example that we saw, Q1 and Q2 are PMOS. So that's one of the differences. Everything else seems pretty much similar. So it's a slight change, right? But most of the logic that we learned, that we studied in the previous example, is applicable here also. Now you notice that because these are NMOS devices, these current mirrors, which are providing bias current to these other transistors, those are at the bottom and they are all NMOS devices. Here the current mirrors are PMOS devices and they are on the top. Okay, so that is one difference. Okay, otherwise it's pretty straightforward. So let's read what the problem says. So there's a two-stage CMOS op amp with 0.18 micrometer technology, and you have your Kn and Kp's. It's a match set because Kn is 4 times. The Vt's are pretty much equal, so that's a good thing. So first, with A and B grounded, so assume that A and B have a ground, perform a DC design that will result in each of Q1, Q2, Q3, Q4 conducting a drain current of 100 microamps. So each of these have to be 100, which means the total bias current will be 200, right? Twice. And each of Q6 and Q7, which is, Q6 and Q7 have a current of 200 microamps. Designed so that all transistors operate at 0.2 overdrive, which is VOV. Specify the W/L ratio required for each MOSFET. So here the W/Ls are not given compared to this problem where we started with the W/Ls and we had to evaluate all these other things including ID. Here he has given us some ID data, but he's asking us to find W/L. Present your results in a tabular form. Next, part B is find the input common mode range, which is similar to what we just saw. Then find the allowable range of the output voltage, so the range of the input and the range on the output, which is determined by the saturation requirements. Lastly, if you apply some kind of input voltage at A and B, which is exactly half of a differential voltage called VID, then find the voltage gain A. So we don't need to know what exactly VID are, but just find the voltage gain VO by VID. Okay, so those are the questions. And just to make things simple again, so we don't spend too much time on this, part B and part C, I'm giving you the definitions. The upper limit of VICM is determined by the need to keep Q1 and Q2 in saturation. The lower limit of ICM is determined by the need to keep Q5 in saturation. And here are the formulas for VICM max, VICM min. Similarly, on the output side, the highest allowable leaves Q6 in saturation. The lowest allowable leaves Q7 from saturation, and these are the formulas. Okay. All right. So let's look at 8108. Now that we know all this, it should be pretty quick, easy to go through it. ID1 is ID2 is 100 and VOV is 0.2. Kn is given. So using this formula ID equals this. Since VOV is also given 0.2, you can find W/L like this for NMOS. Similarly, ID3, ID4, which are these two, which are the common source load. So those currents are also 100 microamps, but they are PMOS devices, right? So that gives you different W/L. Here it's 12.5, here it's 50. They're matched. This is 4 times that. Similarly, W/L for these 578, which are the reference current mirrors, we can find, I haven't shown you the steps, but the same logic gives you 25 for this, and for 6, which is again a PMOS device, you get 100. So in a tabular form, here are all the W/Ls. Okay? With 0 input, ideally the output is also 0. Ideally, right? If everything is matched and there's no offset and leakage and all that. Part B, to find the common mode range, I just showed you what the notes I had given you. So if you apply those, you get ICM max as 0.7, ICM min as minus 0.1. So the range of ICM is minus 0.1 to 0.7. Similarly, on the output side, its VO max is plus 0.7, VO min is minus 0.7. So the range of the output is this. Now, A is equal to A1 into A2, which is the gain. And so first we can find A1, then we can find A2. A1 is pretty simple formula, A2 is the same kind of formula. So you need RO2, RO4, and you need GM, which I've shown you how to calculate. The A1 comes out to be minus 30, A2 comes out to be minus 30. So the total overall gain is the product, which is 900. Okay? All right. So that, and we took half of our time, roughly, That finishes what I had for CMOS op-amp problems. I have given you a few problems to solve in your homework. Please make sure you do it on your own. The CMOS part, I've also, I think, given you at least one BJT problem. Now again, BJT, you may not see too many problems in the exam. I may give you one short question problem, the one for 4 marks in your quiz paper, not the one for 20 marks. So most of the 20 marks questions will be related to MOS technology, but there may be one on BJT in the short form question. Okay, so don't neglect BJTs entirely. You can expect a little bit of it to show up in the test also. All right. So with all that, let's move on to look at some BJT examples. So there is one example, there's actually two examples in the textbook. They're kind of a continuation of each other. One is example 8.6, another is example 8.7. So in 8.6, we have the same 4-stage bipolar op-amp that we discussed all the theory about, right? So this is one stage, this is a second stage, this is a level shifter third stage, and this is the output stage, right? So the 4 stages, and obviously just studying the 4 stages and looking at the circuit diagram is not enough. We need to be able to actually do the circuit analysis and find the voltages and the currents at various points. So that's what he does in example 8.6. 8.7, he continues to show us how to do the input resistance, the voltage gain, and the output resistance. Okay, so this is what is other two examples. Then I picked one problem from the back to do, which is a simple extension again of the same previous problems that we have seen. The only thing is that this resistor R5, remember there is no current source loads, right, in this op-amp. All the loads or are resistances in the collector circuits. So one of these resistances in this R4 collector is being replaced with a constant current source of a 1 milliamp source. If that change is made, then he wants us to recalculate some of the stuff. So that is one problem I picked from the back. After that, I have my favorite project here to do a deep analysis of the audio amplifier, a discrete audio amplifier. Okay, so these are the 4 items in the bipolar op-amp numerical examples. So let's look at each one quickly. All right, give me 1 second, I'll be back. Okay, continuing on, looking at the bipolar 4-stage op-amp example. The notes related to example 6.8.6 are quite clear, okay, and the calculations of all these various currents and voltages is just plain simple arithmetic. There is no calculus, nothing complicated. For example, and I won't read the whole thing, I again expect you to go through each step, make sure you understand what's being said, but he begins the analysis to find all these milliamps and all these volts with one first step, and that first step is to find this current. this is kind of the I reference, right? Based on this current here, you can then get currents to feed this differential stage, to feed this differential stage as the bias currents, and those then flow through these collectors also. So the first step is this. Now how does he find this to be 0.5? So we have minus 15 here, and we know there is a drop of 0.7 here because it's a on transistor. So if you take out that 0.7 from 15, you get 14.3. So we know the voltage here is 14.3. We know the resistance here is 28.6. So voltage divided by resistance gives you 0.5 milliamps as the current. So this 0.5 is also here. Here we have a 4 times multiplier. So this 0.5 multiplied by 4 gives you 2 milliamps. Now this 0.5 splits into 2 halves, right? And assuming Q1, Q2 is perfectly balanced, then the two currents here is 0.25 and 0.25. They add up to 0.5. Now once you know the current here and you know the resistance, you can find this voltage to be plus 10. 0.25 times 20 is 10 volts. Now this 10 volts then becomes the base voltage from which you can continue the analysis. So please go through each step as read the textbook and the notes. Make sure you understand. Of course, if you have any issues, please let me know. No problem. We can work on it together. But generally speaking, I think almost everyone in the class should be able to understand how each of these numbers have been derived. Most of the time, it's just applying Ohm's law. So that's part A. Part B is the power, right? To find the power, there are two sources of voltages. There's plus 15, minus 15. So some of the power comes from here and some of the power comes from there. So he shows you how to add up the positive currents, or the currents coming from the plus 15. Then he shows you how to add up the currents coming from the minus 15. And you multiply the voltage 15 times the current, you get the wattage in each case. So positive wattage is 127.5, negative wattage is 135. If you add the two, it's 262.5, right? Then part C, he talks about calculate the input bias current of the op-amp. So the input bias current of the op-amp is the average of the DC current that flow in the two input terminals, that is in the bases of Q1 and Q2. These two currents are equal because we have assumed matched devices, and the currents are given by IB is IE by beta plus 1, just 2.5 microamps each. Okay. Then lastly, what is the input common mode range of this op-amp? This is similar to all the common mode VICM calculations we have been doing, right? Except in this case, it's for BJTs. And he walks you through how to find the upper limit, that is VICM max. That is based on having Q1 and Q2 in saturation, and where they leave, in active mode. Remember, BJT's saturation is like active, right? So where they leave active mode and enter saturation, that is the point that we are interested in, and he calculates that to be 10.4, and the lower limit he calculates to be minus 14. So read through that, see if I'm sure you can understand it yourself. It's just based on knowing what active mode and saturation mean for BJTs. Alright, so that was example 8.6. The next example, 8.7, is interesting because now that we have seen all the DC bias stuff in the previous example, now we start to determine or understand the working of this as an amplifier, right? You want to know the total voltage gain from the input to the output, and you also want to know what is the input resistance of the op amp and what is the output resistance. So there are many stages. As we know, there's stage 1, stage 2, stage 3, and then the output stage. And each of these stages has its own input and output, and you need to know the inputs and outputs of each stage so that you can find the individual gains of each stage and then the overall gain. So pretty useful and interesting example. I want you again to take some time to go through each one of these steps. He has divided the entire problem into these 4 stages, right? The input stage, the second stage, both these are this is a input stage, this is also a gain stage. So you should expect a high gain there. Then we have the third stage, which we call the level shifting stage, and the fourth stage is the output stage. So the basic formulas he uses for gain is the total gain is the voltage output by voltage input in each stage, which is the total resistance in the collector circuit by the total resistance in the emitter circuit. And so the important thing is to calculate these various input and output resistances. Okay, so for example, the very first input resistance that he calculates is RID, which is as seen between Q1 and Q2, and RID is R pi 1 plus R pi 2. R pi 1 is the input resistance as seen by Q1, and R pi 2 is the input resistance as seen into Q2. And to find R pi 1 and R pi 2, he first finds RE1 and RE2. You can see that RE1 equals RE2 equals 100 ohms. Then he uses the formula. He doesn't show it, but the formula is R pi 1 is beta plus 1, and if beta is 100, then 100 plus 1 is 101. Beta plus 1 times Re gives you R pi. So R pi comes out to be 10.1 K in each case. So to find the gain of the first stage, he shows you the formula A1 equals V output 1 by VID. That means the V output here, and this Ri2 is the input resistance as seen into this stage, the second stage, Q4, Q5 stage. So he shows that as Ri2. And he calculates Ri2 as R pi 4 plus R pi 5, which is these two. And he shows you how to do that. Then he uses the formula A1, the gain is Ri2 in parallel with R1 plus R2, which is this and this, R1 plus R2, divided by Re1 plus Re2. So you can see that the gain of stage 1 is 22.4. Then he finds the gain of stage 2 as minus 59.2 using another set of formulas. Okay. Then the gain of the third stage is minus 6.42. It's not a big gain. And then the last stage has very little gain, roughly 1. And then he takes the product of all 4 to come up with 8513 as the overall gain. Now all these formulas he uses, they are in the table called amplifier. In our chapter we studied called amplifiers for chapters 5 and 6 and 5. So let me quickly show you, for example, for BJTs. MOS amplifiers, yeah, here, right? There's a set of formulas here, and this is on slide 54 of my PPT, but you can go directly to table 5.4 and most of the formulas that he uses here, they in this example 8 point sorry, whichever is the example 8.7, they come from here, from this table. So if you knew this table when you were studying this chapter and you're comfortable with it, you will notice that a lot of the formulas he uses, they look pretty similar to what you see here. Sometimes there's slight differences. For example, this is one by GM, right? He may change that to this one by GM may be RE, because I think somewhere we studied that. Sorry. Yeah. I can spot the exact, sorry, why am I showing you MOSFET? We are studying BJT, right? And the BJT table is here. Yeah, here you can see RE equals alpha by GM. So these formulas are what he uses. That's all I wanted to say. So look at slide 16 of my PPT, or look at table 6.5, and you'll find a lot of the formulas being used. Okay. I don't know that I need to spend any more time on this. So let me move ahead. Now one thing I'll show is the output stage is a emitter follower, right? The other three, these are differential stages, but this one, so make sure that you understand that this is an emitter follower stage. Okay, so that's it. Please take as much time as you need to look through these two examples. This one is a simple variation, so I'm not going to go too deeply into it. 8117 is here, yeah, 8117, and you can read through my steps directly, no problem. But the last thing that I wanted to talk about in the next 2 minutes is that this problem of creating an audio amplifier is very similar to what he just walked us through on the 4-stage bipolar op amp. The only difference is I don't have, for this design, there is no differential amplifier. It's just a regular emitter follower input stage, two common emitters here to form the gain stage, and one output stage, which is also an emitter follower. So if you go through, I won't have time to walk through every step, but the analysis is pretty similar to what he showed us for different stages. So stage 1 is the input or buffer stage, it's an emitter follower. Stage 2 is a gain stage. Stage 3 is an output stage. So how do you go about creating a design? Because all you are told is, hey, give me an audio amplifier. The input signal is 10 millivolts peak and it has a 10K source resistance. The output wattage has to be 0.1 watts going into an 8 ohm speaker, right? That's all you've been told. So based on that, you have to make a lot of assumptions. You have a lot of freedom to pick things. So for stage 1, for example, I pick a transistor that's 100. I pick a bias current that's 1 milliamp. Because we are operating off of 12 volt supplies, I pick a VCE, which is about 6 volts. Then I have to prepare this bias resistance. So I pick a RB1, which is R1 in parallel with R2 of 100K. So based on all that, I come up with the small signal gain, this formula, and I need R in 1, I need small re, RB. So using all that, I come up with a gain of 0.892 for the first stage. Then I design the last stage, the output stage. I make some assumption. Remember, this is a power transistor, right? Higher amps flow through it. For example, the load current comes out to be 0.158 amps or 158 milliamps, which is much higher than the 1 milliamps we normally use, right, as bias current for a transistor. So this is a power stage. So I picked a transistor with a beta, lower beta. I picked a beta of 50, and then IE4, which is twice of the I load. And for that, finally, I get a gain of 0.984. So I have the input and the output gains. Now I need the gain of the middle. So I come up with the gain required in the middle as 144. Now I can't get 144 in one transistor, so I'm going to use two transistors. One of them has 5 and one of them has 28.8. So if I multiply the two, I get a gain of 144. Then I create this circuit, which is connected to each other. The coupling is through a capacitor. And applying the same method and applying the same formulas, generally, I find the values of the collector resistances and the emitter resistances, right? And finally, I summarize all the values of the amplification and the resistances in this neat table. So the design is complete. Okay. So that's how you would do an audio amplifier design. Please look through this. The formulas are all what we already know. There's nothing new. And if you do run into any problem, give me a buzz and we can discuss it. Okay? Thank you. Take care. Bye. With that, we finish chapter 8.